welcome back to online lecture series on nanotechnology and surface engineering. We have already started this chapter and we have seen couple of methods or tools to characterize the nanomaterials. First of all, we will go through a quick revision of the topics that we have already discussed. So this is the summary of the chapter, in which there are total 5 tools that we are going to discuss, and out of that we have already discussed about X-ray diffraction and scanning electron microscopy. So let's have a quick look on what we have already done in our previous class. First, we discussed about optical spectrometry, that is, it uses the interaction of light with the matter as a function of wavelength or energy, so that we can obtain the information or details about the material. We penetrate up to 50 nanometer, and this is very famous technique or tool to analyze the material, because it is comparatively much faster and it is non-destructive, as well as it provides the high quality images. So this is the principle that we have discussed in our previous class for X-ray diffraction, and these are the characteristics or the formula based on which this method works. Then we discussed about scanning electron microscope. Here, this is the principle that we have discussed, that the specimen is kept at the bottom and we generate an electron beam through an electron gun. We have anode and magnetic lens in between, and after that we have scanning coils and the electron detector which sends the signal to the TV scanner. These are the details that can be achieved, that is topography, morphography, composition and crystalline structure. Then the 3 operation modes. First is primary, secondary and then tertiary. This is again the same figure in a different way. There are few advantages and disadvantages that we have already discussed in our previous class. So now we are going to discuss about transmission electron microscopy, that is TEM, in this lecture, as well as we will try to have a look on atomic force microscopy. So let's discuss about transmission electron microscopy. This is the actual device for this method, and first of all let's discuss about what exactly we can see using transmission electron microscopy. 3 things that can be checked here. First is morphology, that is we can get details about shape, size and order of particles in a sample. Then we can have crystalline structure, that is arrangement of atoms in the sample, as well as defects in the crystalline structure. Third thing that can be known through this method is composition of a material, that is elemental composition of the sample. So these are the 3 things that can be checked using transmission electron microscopy. Now let us discuss about the basic principle of this method. So here, first of all, let us see this figure. So unlike previous method, here the specimen is kept in between. In previous method the specimen was kept at the bottom. Here we are having it in between. So as usual we are having an electron gun and cathode, and then we are having a condenser lens So after the condenser lens, we have an objective aperture lens, and in between these two lenses we are keeping our specimen, that is over here. After that we are having one more lens, that is known as intermediate lens, and after that the projector lens. At the bottom we have fluorescent screen. So there are around total 4 lenses which are present in this entire arrangement. First is condenser lens, then in between we have some specimen, after that we have objective aperture lens, and then intermediate lens, and last one is the projector lens. So here the crystalline sample that interacts with the electron beam, that is through the electron gun, mostly by diffraction rather than the absorption method. So here majority of the electron beam interact with the specimen through diffraction method. The intensity of diffraction depends on the orientation of planes of atoms in the crystal relative to the electron beam. So the orientation is very much important in this case, that how much diffraction will happen, it depends on the orientation of the planes of the atoms in that particular crystal. And here with this method a high contrast image can be formed by blocking a high contrast image can be formed by blocking deflected electrons, which produces a variation in the electron intensity that reveals the information on the crystalline structure. So here this electrons, the deflected electrons can be blocked. That will provide a variation in the electron intensity. So this will give us the details about the crystal structure. This can generate both bright or light field and dark field images. So a variety of images can be obtained using this method. Now as usual we do have some advantages as well as some disadvantages. Let's first discuss about the advantages. The first advantage is additional analysis techniques like X-ray spectrometry are possible with the help of STEM. So we can have some additional analysis. Second is high resolution images that we have already discussed in our previous slide. The third one is 3-dimensional image construction is possible. However, it is aberrant. Fourth is changes in the nanoparticle structure as a result of interactions with gas, liquid or solid phase substrates can also be monitored. So some kind of variation in nanoparticle structure can also be obtained with the help of this method. Now let us discuss about some disadvantages. First of all, the sample must be able to withstand the electron beam and also the high vacuum chamber. So that is one requirement. Second is the sample penetration is necessary, which is mostly used for 2-dimensional images. So we need some form of sample preparation for this method. And third is this methodology is a bit time consuming. Now the next method is atomic force microscopy. So before that let's go back here, that what we discussed in transmission electron microscopy, that we can obtain the morphology, crystalline structure and composition. Then this is the basic principle, and this method primarily works on the diffraction of the electron beams, not on the absorption. Then we already discussed about the advantages and disadvantages. Now let us discuss about our next method, that is fourth tool for characterizing the nanomaterial, that is atomic force microscopy, and it is also known as AFM. So here the signal that is generated from short range forces between the tip and the sample. So here in this case we are having one tool that is having a tip. So some force is applied on the sample through this tip, and we see the forces between the tip and the specimen. Like there are van der Waals force, then capillary force and electrostatic force. So these are the forces which are calculated here, and there is 1 nanometer lateral resolution and 0.1 nanometer depth resolution in this method. There are two kinds of mode. First is contact mode and second is tapping mode. Now this graph is interesting. I am currently also explaining this graph. However, you will understand this graph more detail when we go to the arrangement of this entire system. So here on the x-axis we are having the distance, that is tip to sample separation, and on the y-axis we are having this force. So as you can see, there are two regions. First is intermittent contact, that is close contact, and then we are having a non-contact. When the force is positive, it is considered as a repulsive force, and when the force is negative, then it is considered as attractive force. So when the distance is almost nearly zero, then this repulsive force immediately reduces and it becomes zero over here. Then once the distance increases, that is tip to sample distance increases, then the attractive forces increases, and up to certain limit it becomes maximum on the negative side. That is, attractive forces are maximum over this region, and then when we increase the distance between tip to sample, then this attractive force keeps on decreasing, and after certain region it becomes nearly or approximately zero. So this is the graph between the tip to sample distance and the force. We will see this in much detail now. So these are the few images. Just wait. So these are the few images. Just a moment. So let us continue now. Here these are the AFM components. If you see carefully here, then this is the AFM cantilever, and this is the tip of that cantilever, and here we are having this sample, and this elliptical shape is the sample stage. Now here from this portion the electron beam is incident on this AFM cantilever and it is received by this 4-quadrant photodetector. Here also you can see the actual image of this cantilever with the tip, and from this 4-quadrant photodetector a feedback is given to this sample stage. And if we discuss the cantilever to be specific, then here we are having this length of the cantilever and this is the thickness with the tip. So cantilever dimensions determine how easy it is to bend. Here are few images. That is, the image quality depends on the tip size and shape. So here you can see this sample surface and the tip. These are the various examples. And then we have this influence of tip sharpness, that is, here we are having this trace and here we have a tip. So in first figure the tip is much more sharper than the second one. So this is also one more figure of contact mode and tapping mode. So we will discuss both of them. So first let us discuss about contact mode AFM. So here the tip of the cantilever is in contact with the specimen surface, and deflection of cantilever is the feedback in this case. So here we are having a laser which is incident on this tip, and here we are having the detector which is receiving the diffraction. Then we have a tapping mode, the figure that we discussed over here. So in case of tapping we have a piezoelectric material which drives the oscillation. So in this case this cantilever along with the tip is having some form of oscillation through piezoelectric materials, so that it can continuously tap on that surface, that is specimen surface. So here we can see that this tapping can be in the range of 10 to 100 nanometers distance, and this piezo here the laser is, this dotted line is the laser beam, and the refracted laser is received here by the detector, and the surface acts to damp the resonance, and here the feedback is oscillation amplitude. In previous case the feedback was deflection of cantilever, and in this case the feedback is oscillation amplitude. And this figure we have already discussed, if you recall, we have already discussed this figure, and the cantilever oscillates can be driven at a resonant frequency of 100 to 500 kilohertz. So that is the atomic force microscopy, and the next topic is UV or ultraviolet or visible spectroscopy. This we are going to discuss in our next lecture. So let's quickly revise what exactly we have done in today's class. Today we have discussed these two methods, that is transmission electron microscopy, also known as TEM, and the second one is atomic force microscopy. We have discussed these two methods in today's class. So this is the transmission electron microscopy. It is used for obtaining the morphology, crystalline structure and composition. We also discussed the basic principle, advantages, disadvantages, and we discussed about atomic force microscopy with two modes, that is contact mode and tapping mode. It is essentially having a cantilever along with a sharp tip and a laser beam and a detector. Here is the contact mode, and then the next is tapping mode. So this is the end of today's lecture. Thank you for watching this video.